Hello everyone and welcome back to continuous function. The second section we're going to now compute where a function is continuous using our brand new definition, of course, but we're really going to compute it. So this means no more graphs, no more little square roots or semicircles. We want to compute where a function is continuous. This might sound like a very difficult challenge to start with because computing where a function is continuous would initially mean, well, for any point within the domain, compute the two-side limit and check if it's equal to the output. If your domain starts somewhere, you have to compute the right limit and check if it's equal to the output. And same thing, if there's an endpoint, you have to compute the left limit and check if it's equal to the output. That's a lot of work. So what we're going to do first is introduce a very powerful theorem that is going to really cut the crap a lot for most of our question. And this theorem is the following. If your function is defined by only one equation, so this means that it's a finite combination of addition, subtraction, multiplication, division, or for functions, you can also create new function by composing them. So by composition of basic terms. What I mean by basic terms are power functions, the exponential function, the sine function, the cosine function, and even their inverses. So the logarithmic function, the arcsine, arccos, and etc. Then it's a very, very powerful result. If you have to compute where is a function is continuous, you only have to compute its domain. Say what? So it's like all the crap that we just did. So for one equations is really reduced to computing where the function is defined. So this is kind of a magical moment for us because this definition that we just introduced in the previous section, where you have to adjust yourself, that captured the intuitive definition. Not only does it capture the intuitive definition that we want to know where we can draw a function without lifting our pen, if we want to compute it, it goes back to simply computing the domain. Of course, when I say simply, you have to be careful. Computing the domain is, of course, sometimes quite challenging too. So let's just look at an example. So here's a classic question. We want to compute where the function root of square root of x, square root of 7 minus x, divided by ln of x plus 13 is continuous. So the first thing to realize here, is what this function is given by only one equation. So boom, so f of x is one equation. So cont f is going to be equal to dom f, though. So that's really, really powerful. So we just need to compute its domain. So this is very standard stuff. So I'm not going to spend too much time on it. But first, of course, is there's a square root. So here, square root of a. So this means that inside the square root, things needs to be strictly bigger than 0. So if you isolate x here, this means that x needs to be less or equal than 7. There's also a logarithmic term. So we know for logarithmic term, the inside needs to be strictly bigger than 0. So this leads to x being bigger or equal than minus 13. So be careful when the ln is down there. So I know, of course, you might have experienced this recently. So when the ln is at the denominator, it could be equal to 0. So you don't want that. So here we're going to get a division if the ln is equal to 0. So we don't want it to be equal to 0. So we don't want the inside to be equal to 1. And if we do this, so here we go, poof. So for the division by 0 here, we don't want the logarithmic term to be 0, so we don't want the inside to be 1, so we don't want the x to be minus 12. So if you combine all that stuff together, so less or equal than 7, strictly bigger than 13, but then minus 13, but not minus 12, you get that the domain is the interval from minus 13 to minus 12 open, union minus 12 open to 7 close, and then for free, after going through hell of computing the domain, you get what? You get that this is also cont f. So you get where it's continuous. So very, very powerful result. If you have one equation, a function defined by one equation, if you need to compute where it's continuous, just compute its domain. Voila. So chapter 3 is So magical. It's incredible. So, small remark before moving on to our next example where we will create trouble. For our functions defined by one equation, like I said, domain is where the function is continuous. But if you have a piecewise defined function, then things are going to be a bit more interesting, because if the function changes equation, then you're no longer guaranteed that the domain will be the same thing as where a function is continuous. There's a lot of piecewise defined functions that are defined everywhere, but they're broken into pieces. Okay, so for piecewise defined function, things are going to be much more challenging, and typically those are the questions we're going to ask you to work with, because as you saw with the previous example, when a function is defined by one equation, there's no new computation. Okay, so piecewise defined function will be trouble for us. So interesting for us. All right, first example where we're going to study where a function is continuous for a piecewise defined function. So this is really a classic question of chapter 3. So suppose f of x is x squared if x is strictly less than 1, and suppose that it's root of x plus k if x is greater or equal than 1. So if possible, find the value of k that will make this function continuous everywhere. So classic question here. So first, this function is defined by two equations. So first, what you should do is figure out where the equations themselves are continuous, and then see how f is using that in order to get information about the continuity of your function f. So first thing here, so my function is changing equation where, so it's changing equation around 1. So you write that down. This is very, very important. You need to show me that you understand that this f is not x squared. It's not the square root of x plus k. It's a function that changes equation from x squared to the root of x plus k at 1. So the first thing you say here, boom, f of x changes equations at x equal 1. So you need to write that down. So it needs to be clear. All right, so because it changes equation around 1, you need to break your analysis of the function into 3 parts: before 1, after 1, and at 1. And always do it in that order. Okay, so I'm really, really strict. So let's look at what's going on before. So before 1, the function is following x squared. So here we go, poof. So before, oh, sorry, I said poof, but I went too fast here. So before, oh, here we go. Hello, technical difficulties here. Okay, so here we go. So poof, so before, okay, since what do we have before? We have x squared, and we know x squared is continuous everywhere. Okay, x squared, no division, no square root, no bullshit. Okay, so here x squared is continuous on air, so on R, so on air, hey, on air, whatever. So because it's continuous everywhere, what does it mean for f? Well, because f is writing that function before 1, you can automatically conclude right away that f of x is continuous before 1. So remember, we're doing the analysis before here, so it's continuous for x strictly less than 1. Okay, so it's always strictly before, strictly after. Don't worry about where the equality is. So the before is really before, and the after is really after. So what's happening now after? So after here, so after, here we go. So here, poof. So after, we're following the function root of x plus k. So here it does not really matter what k is. We know the square root of x is continuous from 0 to infinity. Again, I forgot to mention this, but I'm really using the previous theorem already. So I know the domain of x squared is everything. So that's why it's continuous on everything. I know the domain of root of x plus k is continuous for 0 to infinity. So I can, so because the domain is that, it's also continuous there. So what does it mean for f? Because f is only writing it starting at 1, you can say that f of x is continuous. There we go. So f of x, hello, okay, sorry. So f of x is continuous for x. And here it's strictly bigger, like don't be fooled. We're really looking at strictly before, strictly after. And now this is where the question kind of takes shape. What's going on at 1? So at 1, there's 3 things to compute now. So we want to check if it's continuous at 1. 1 is within the domain. So I forgot to mention this here, but when we think about the domain of f, so the domain of the original function, f, The domain is everything. Domain of f is r. Okay, so there's no way you can make this function crash. You say, oh, well, if x is -1, the square root, like, shut up. If x is -1, you're using x squared. So there's no way you can make that function crash. Okay, the domain is everything. So it means that when we're computing where the function is continuous, we have to use the two-side limit. So at 1, there's 3 things you need to compute. You need to compute the output, the left and the right limit. And you need to make sure, if possible, that all these things are equal. So for a point where the function changes, you're always going to have the following setup. So at 1, poof, you're going to compute f at 1, the left limit at 1, and the right limit at 1 of f of x. Everything is using f initially. And here, the only challenge with these questions is just writing the solution correctly. There's not a lot of difficult computation, but there's a lot of theory that you're using that you need to write down properly. Okay, so the structure of the solution is absolutely crucial in these questions. So what's the output at 1? So here, the output at 1, if I look at my piecewise defined function, I'm going to use the second function. So the output at 1 is simply root of 1 plus k, which will give me 1 plus k. So that's just computing the output using the piecewise defined function. What is the left limit of f? So here I'm going to use the whole equal principle. So f is not x squared or the root of x plus k. It's a combination of those two functions. But on the left side, f only uses x squared. So I can use the whole equal principle to say that the limit as x approaches 1 minus is the same as the limit as x approaches 1 minus of x squared. Now you can plug 1 in, not 1 minus. There's no reason for that. And 1 squared is just 1. So I compute my left side limit using the whole equal principle. And then on the right side, so the limit as x approaches 1 plus of f, on the right side, my function f is using the equation root of x plus k. So I'm going to use the limit as x approaches 1 plus of root of x plus k. And I'm going to plug 1 in it. And you're going to get the root of 1 plus k, which gives you 1 plus k. So you're getting three things here, and you want all of them to be equal. So what you do is you just set these 3 things equal to each other, and you try to find a value of k that will make this possible. So here I want 1 plus k to be equal to 1 to be equal to 1 plus k. So this creates the following, this induces the following equation. You want 1 to be equal to 1 plus k because there's 2 1 plus k's here. And then if you isolate k here, you get that k is going to be 0. So this means, in conclusion, that our function is continuous everywhere if and only if k is equal to 0. So boom. Okay, so here's my conclusion. F of x is continuous on R if and only if k is equal to 0. If k is anything else, then it's not going to be continuous at 1. It's still going to be continuous before 1 and after 1, but it's not going to be continuous at 1. So again here, so just in a nutshell, I'm going to repeat myself, but it's because this is the meat of those solutions. So first, identify where your function changes equation, and then you do analysis before and after. Because before and after, typically you're just using one equation. You can just use the domain to really compute directly where the function is continuous for a lot of values on intervals and stuff like that. And then at 1, this is where you have to really put a little emphasis on details. So at 1, you need to compute the output, left and right limit. Typically, these are whole equal principle questions where you just replace f by the equation that it's using on the left and the right side, respectively. You compute outputs. You just set everything equal to each other. You hope for equality. If I throw in the mix some constant or some coefficients, then, of course, you try to solve for those that will make these two sides equal to each other, okay, and equal to the output. Sometimes it won't work, though. But anyways, for that example, that's it. All right, let's do another example. Suppose f is e to the x for x less or equal than 0, and it's 1 over x plus k if x is strictly bigger than 0. Find, if possible, the value of k that will make this function continuous everywhere. So, of course, I'm using 2 equations. Where does it change equations? So you have to make sure that you are clear with what's going on. So here we know the function changes equation at 0. So I need to do analysis before 0, after 0, and at 0. So again here, I always forget this, but if you're computing the domain of this function, it's continuous everywhere. Okay, so there's no way you can make this function. Well, what about 0? At 0, you're using ex. E to the 0 is 1. So there's no way you can make f crash. Okay, so, all right, so let's do our analysis before and after. So what's going on before? So here, f of x before 0 is using the equation e to the x. So what do we have here? Poof, we have the following. So here's the line. This is always, it's very typical for those questions. So before, ex is a function that is continuous everywhere, and because f is using it before 0, we know it's continuous before 0. So before 0, there's no trouble. What about after? Well, after f of x is using the equation 1 over x plus k. So here, of course, 1 over x plus k crashes at 0. So, but that's the only place it can crash. So here, when you're trying to compute where the equation is continuous, well, just using the domain here, we know that 1 over x plus k is continuous on everything but 0. But this means for f, though, it's continuous strictly after 0. So remember, there's a distinction between the equation, where the equation is continuous, and where f is using it. So because there's only a restriction at 0, but f is not using it at 0, we know that after there's no trouble. So before 0, no trouble. After 0, no trouble. F is continuous. And here, make sure that you see that the before and after for f, the inequalities are always strict. You don't care where the equality symbol is used here. Everything is strict with respect to f of x. Now the big game. Okay, so what's going on at 0? So remember, and this is really, really crucial. The first thing you do at that point where it changes equation, you first compute, or you set up. So at 0, you need to compute the output. You need to compute the left limit around 0 of f, and compute the right limit of 0 of f. So it's always f first. You don't put any equation. This is really crucial. This is the number one spot where people lose marks. So at 0, I'm going to use e to the 0. So here, I'm going to use e to the 0, and that gives me 1. What about the left limit? Well, on the left side, I'm using ex, so I can use the Hoyle principle and get that this limit is the same as the limit as x approaches 0 minus of f of x, not f of x, of e of x. So I'm replacing f by its formula on the left side. Now I can replace x by 0, not 0 minus, just 0. There's no trouble here. And e to the 0 is 1. Now, what about the right limit? So on the right side, I'm using the equation 1 over x plus k. So the limit on the right side for f will be, by the Hoyle principle, the same as the limit as x approaches 0 plus of 1 over x plus k. So here we cannot just put 0. Why? Because if we put 0, we would get a division by 0. So here, normally I like to explain why on top of the equality. So here, poof. Okay, so we have a bad 1 over 0 problem. So this is my green light. You need to put that down somewhere so that you can put in 0 plus. So you get 1 over 0 plus k. 1 over 0 plus is infinity, and infinity plus k will be infinity. So now when you compare everything, what's going to happen? So we're trying to find a k that will make all of these three equal to each other, but you can see here that there's no way 1 is going to be equal to infinity. There's no k that's going to fix this. So sadly here, we're not going to get inequality for any k value. So this means that f of x is never going to be continuous. So it's not continuous at x equal 0. So therefore here, so it does not matter what k is, okay? So this function here, my conclusion is the following, poof, okay? So f of x is continuous on everywhere except at 0 for all k. And here, I like this example just to illustrate, okay, that the function here is defined everywhere. So the domain is everything, but it's not continuous everywhere. So there's a nice distinction here to see. Okay, so anyways, so again here, for the structure of those questions, for piecewise defined function, find where it changes equation, compute the domain of the equation before, use that to say where the equation is continuous, and then to conclude if the function f is continuous before, and then do the same thing after, use the domain for the equation, and then look at where f is using it, and then at the point of change, output left and right limit, compare, and check if they're all equal for continuity for that point. Okay. But anyways, for that section, that's it. That's all. Bye-bye.